So we're now ready to continue our discussion of the coordination methods that are part of Java built-in monitor objects. And we're going to talk about how you can use these coordination methods to provide waiting and notification mechanisms that enable threads running in a concurrent program to schedule and coordinate their interactions. And we'll see that this is crucially important to understanding the concept of a so-called monitor object. So earlier in previous lessons, we talked about how Java synchronized methods and synchronized statements only provide a partial solution for concurrent programs. And what we're going to do now is we're going to show how these other mechanisms, the wait and notification methods, allow threads to coordinate their interactions in ways that are more sophisticated and often more efficient than using busy waiting and synchronizers in isolation. So the three methods that we're going to be concerned with here: the wait method, the notify method, and the notify all method. And these methods are all provided by the Java object superclass, which is the root of all classes in Java. So as you can see here, the wait method causes the current thread to block and to wait until another thread will call the notify method or the notify all method for this particular object. This is very much like the await call with Java condition objects. There's also a notify method, which wakes up a single thread that's waiting on this object's monitor condition. And this is very much like the signal method for Java condition objects. And then finally, we have the notify all method, which wakes up all threads that are waiting on this object's monitor. And not surprisingly, this is quite a bit like the signal all method for Java condition objects. You have to beware of the thundering herd problem when you use notify all. And as we'll see a little bit later when we talk in more detail about how these mechanisms work, notify all ends up being used quite a bit in Java built-in monitor objects, which is one of the reasons why it's a limited interface and often should be deprecated in favor of using the more modern Java condition object. Java built-in monitor objects have exactly one entrance queue and exactly one wait queue. And if you take a look at the Wikipedia link for monitor, you'll see that there's something called implicit condition variable monitors, and that's the kind of monitor that Java supports. As you can see, the entrance queue is used to serialize thread access into the monitor object's critical section, and this is inevitably done by either defining a method in a monitor object to either be synchronized and have the entire body of the method be the critical section, or by using synchronized statements where you have a subset of the method's body be a synchronized critical section. So that's how you do that. Should be no surprise at this point, but we'll see some more examples here shortly. Then we have the wait queue, and all threads that call wait on a given monitor object will be parked on the wait queue, waiting to be notified when conditions changed that may be more to their liking so they can proceed. All the notify and notify all calls apply to the wait queue, and basically they either take one waiter or all the waiters and move them from the wait queue into the entrance queue so they can go ahead and actually run. So here's a simple example. This is the simple bounded blocking queue example, which is just another variant of what we've been looking at so far, where we had our buggy queue and our busy synchronized queue and so on. This is now the bounded blocking queue. And this implementation fixes the busy waiting problem that we had with the busy synchronized queue. If you remember the busy synchronized queue from several lessons ago, that was correct in the sense that it would give you the right results, but it would sit there and sort of neurotically spin over and over again, waiting to get the lock, which is undesirable for obvious reasons in many cases. So as you can see, the put method for our simple bounded blocking queue uses the guarded suspension pattern, very much like we saw when we talked about condition object. And in this case, if you try to put a message into a full queue, then we're going to go ahead and go to sleep or wait until the queue may be not full. And just a couple other things real quick. You can see this particular implementation uses a synchronized statement. So we synchronize on this. I don't have to do it that way. I could synchronize on some other field if I wanted to, as long as it was a reference type, but I'm just making it simple. And so in this particular case, while is full returns true, we're going to wait, and that will then put that calling thread to sleep and release the synchronized lock on the implicit lock. So once we get through the guard here, once the queue is no longer full, then this implementation will add the message to the list, because we're using a linked list in this case, and then it'll go ahead and notify all the waiters to wake up and see if they can make progress. And the reason why we have to use notify all here is because we only have one monitor condition that is being used for both the not empty and the not full conditions. And so the whole uniform waiters test that we talked about when we talked about condition objects doesn't apply here. We have non-uniform waiters because some waiters are waiting for the queue to be not empty, some waiters are waiting for the queue to be not full, and we can't differentiate between them with multiple condition objects because there's only one condition variable per built-in Java monitor object, which again is a limitation. And this is just due to those weird quirks that came in the original Java synchronizer mechanisms that were there from Java 1 onwards. And if you want to read more about all this stuff and why you have to do it this way, take a look at this Stack Overflow discussion, which is really quite enlightening. The take method is kind of the inverse of put. As you can see here, it calls wait when the queue is empty. And what it'll do is uses the same basic monitor object trick. We block on the entrance queue with synchronize this until we get ourselves exclusive access to the critical section. And then while the queue is empty, we have to wait because we're trying to get back an item, and you can't get an item back from an empty queue. So that again will atomically release the implicit lock and then go to sleep on the wait queue. Once we make our way through this guarded suspension region of code, then we will notify everybody they can wake up. And we have to use notify all again because of the fact that there's only one condition variable per Java monitor object, which is a limitation. And we'll talk about the mechanisms here in a little bit more detail when we go into the nitty-gritty of how all this stuff works. And I should also hasten to point out that the last thing we do is we return the front item from the queue. So that goes ahead and returns the item that was first on the queue. Now, the way that these built-in monitor objects and their synchronizers are implemented under the hood is typically by using POSIX synchronizers or some other variant. For example, if you're on Windows, they have other synchronizers, but it's basically the same kind of idea. So, for example, the entrance queue could be implemented by a POSIX recursive mutex, very common thing to do, which is just a recursive mutex or a reentrant mutex that's implemented in C as opposed to Java. And the wait queue is typically implemented using some variant of a Java condition variable, which is, again, is a C-based set of APIs that give you condition variable semantics. And those semantics then will queue up the threads in a wait set, waiting for their chance to make forward progress. The Java condition object is very similar to the POSIX condition variable, just a little difference in syntax because it's different languages. The implementation in Oracle's JDK uses low-level locking primitives. If you take a look, you can actually find the source code for all of this stuff. If you want to see how it's implemented, you can take a look and see how it works under the hood. But these are basically the methods that are used. There are different ways to do this, and some work one way, some work another, but they're all basically variants of the same implementation pattern.